Okay, so these series of talks over the next couple of months were originally going to be talks at JuMP-dev in Belgium, but since we've had to cancel this, we're now going to have some of the talks remotely in these monthly calls. And first up, we have Guillaume, who's going to talk about the design and features of Coluna. So take it away.
Thank you. Thank you for this opportunity to present the work we've done on Coluna. So my name is Guillaume Marques. I'm a PhD student at University of Bordeaux in France. And this is a joint work with Vitor, Ruslan, François, and some contributors who help us to develop some features. So I'm going to talk about the design and the features of Coluna. But first, what is Coluna? It's a framework to optimize integer linear programs that you can decompose. It means that if you remove the linking constraints or the linking variables, you will have blocks that you can solve independently. So if you apply Danzig-Wolf decomposition, the linking constraints, the violation of the linking constraints will be penalized in the objective function, and you can solve the block independently. For the Benders decomposition, you fix the complicated variables in the range column, and then you can solve the blue block independently. So now it works only if the variable in the blue blocks are continuous, so it's standard Benders decomposition. But in the future, we hope that it will work with integer variables at the second level. And in the future, we would like to do a combination of Danzig-Wolf and Benders decomposition, and also nested decomposition. It means that you can decompose inside the blue blocks. So the main goal is to take advantage of the structure of the problem. Okay. So this is an overview of how it works. So first, the user writes the model with JuMP and block decomposition. Then when the user call optimize, block decomposition will annotate the variables and the constraints. So the annotation, it's the sub-problems in which the variables and the constraints are. And then Coluna reformulates the problem and run the branch and cut and price algorithm. So I'm going to present these 4 steps through a simple example, the generalized assignment problem. So in this problem, you have a set G of jobs and a set M of machines. And the goal is to assign the jobs to the machines at minimum cost. So this is the mathematical model. XMG is the variable. It's equal 1 if you assign job G to machine M. And you have first, you have set partitioning constraints for each job. So each job must be assigned to one machine. And then you have one knapsack constraints for each machine. So this is the JuMP model. So it's the same, obviously. And you see that if you remove the linking, the set partitioning constraints, you will have M independent knapsack problems, and the knapsack problem is tractable. So we are going to do a Danzig-Wolf decomposition over the machines. And to do that, so you need block decomposition. You replace the model by a block model. Then you declare the set of machine. So you declare M as the index set of the subproblems. So one subproblems for each machine. And in fact, M will be an array of axis ID. And when block decomposition will look at the indices of the variables and constraints, each time it sees an axis ID, it knows that it goes into a subproblems. The JuMP model stays is the same. So we don't touch the JuMP model. And at the end, we do a Danzig-Wolf decomposition over the machines. So this macro here will create one annotation for each problem. And these annotations are stored in a tree. So the master will be the root node, and the Danzig-Wolf pricing subproblem will be the leaves. So in fact, it's not very useful when you do simple decomposition, but it will be useful with a nested decomposition. And here dec will be a new variable that points to the root of the decomposition tree. Okay. So if you have a very good algorithm to solve the knapsack problem, you may want to use the pricing callback because inside you can call your algorithm. In that case, you don't need to define the subproblem constraints in the JuMP model because they are implicitly defined by your algorithm. So it works like the heuristic callback in JuMP. So you create a new function. Inside, you retrieve the ID of the subproblem, the reduced cost of the subproblem's variables. You solve the knapsack problem with your algorithm, and then you submit the solution. So the cost and the description of the column. So you have to specify that the solver of the subproblems will be the pricing callbacks, and you can instead of using a pricing callback, you can use an optimizer. So you can mix the optimizer, the pricing callbacks. You do whatever you want. Okay, so the user wrote the model with JuMP and block decomposition. Now he calls optimize, and block decomposition will do the annotation of the variable and the constraints. In fact, these are attributes of the variables and the constraints. So when optimize call this method in block decomposition, just after you will have an annotation for each variable and each constraint. So here you can see that the knapsack constraints of machine 1 will be in the subproblems with ID 3. And the variable for the machine 1 job 1 will be in the same subproblem. For machine 2, it will be in the second subproblems, and the subpartitioning constraints of job 1 will be in the master. So you can check if the decomposition is correct. Here, it's the good decomposition. Okay. And now, Coluna retrieve the models and create the reformulation. So it's a Danzig-Wolf reformulation. So you will have a master problem with an exponential number of variables and one subproblem for each machine. So you will solve this problem with column generation. For each machine, the subproblems will generate the best, the assignment pattern that has the best reduced cost. So that improves the best the master. And we solve the continuous relaxation of the master. We compute the reduced cost until the algorithm converges. So this reformulation is stored in a very simple structure. So it's a reformulation with the master, a collection of Danzig-Wolf pricing subproblems, and a collection of bundle separation subproblems. So it's a very simple structure, and most of the algorithm in Coluna takes this structure as input. So it's a very important one. And so you can see we have also a formulation. Formulation, it's the formulation with the coefficient matrix, the constraints, the variables. It's the representation of the formulation in Coluna. Okay. And then Coluna runs the branch and cut and price algorithm on the reformulation. So the branch and cut and price, it's a branch and bound with cut generation and column generation. So this is the constructor to parameterize the algorithm. So it's a tree search algorithm with 3 algorithms inside. The conquer algorithm to optimize the reformulation at each node of the branching tree, the divide algorithm that will generate the branching constraints at each node, and then the explore strategy. It's the way you want to explore the branching tree. So you have nested algorithm, and you can parameterize until the leaves. I'm not sure if it's clear, but I will see you an example just after. And so you have to give this algorithm here. It's the solver keyword of params, and the default optimizer, it will be the default solver for the master and the subprograms. So here it's Gurobi. So Coluna provides several algorithms. They are simple algorithms. They just call the solver like Gurobi, VMY, or the callbacks, and more advanced algorithms that are a combination of simple algorithm with specific operations. So for instance, the column generation, it will solve the continuous relaxation of the master with solve LP form that called Gurobi. Then we compute the reduced cost of the subprograms variables, and we solve the pricing subprograms by calling solve IP form for it that calls the pricing callback or the subsolver. And call-gen conquer will call column generation. When it converges, it looks for violated inequality with cut callback. If there are violated inequalities, we run again column generation. Otherwise, we try to improve the master with solve IP form. So the goal is to avoid duplication of code. So it's just software good practices, but that's the goal. And when you define the parameters, you can so it's a nested it's a nested constructor. So you can define the parameters of solve LP form. Okay. And you can define a new algorithm. So there is an interface, but I will not go into details, and the name may change. Abstract algorithm, they are the parameters. Abstract data, it contains the reformulation and additional data, but we have to change this name because it can be anything. And we have input and output. Okay. So that's an overview of the Coluna environment. And here you can see that you define the model with JuMP and block decomposition. Then Coluna solve it using subroutines via a Mathopt interface or directly using Julia code. So you can see that Coluna relies on Mathopt interface. So I think it's fair to say that without Mathopt interface, Coluna will not exist. Okay. And inside Coluna, there is two submodules. One algorithm that contains algorithms, it's obvious, and matprog that contains representations of formulation and reformulations. And inside matprogs, we use a package, dynamic sparse arrays. Since we are doing column and row generation, we need a very efficient data structure to store the coefficient matrix. So that's the goal of dynamic sparse arrays. And it's one of our package. Okay, so Coluna, it's 2 years old now. It took more than a year to develop a good enough prototype. And last month, we were focusing on the performance, the design, and new features. So right now, the Danzig-Wolf reformulation is available. You can run the branch and cut and price with stabilization to make the column generation faster. With strong branching, the pricing callback. With the robust cut callback, it's the user cut pricing. It's the user cut callback from JuMP. And there is some alpha features like subprograms parallelization, columns cleanup, and bundles reformulation. Very soon, we will have automatic decomposition inside block decomposition. So this is a student from Aachen University that's working on it, David Michael. And we are going to develop non-robust cut callback and heuristic, the diving, and the preprocessing is in development. For the future, maybe next year, I don't know, the parallelization of the branching tree, the combination of bundles and Danzig-Wolf and nested decomposition. So this is those features, it's a lot of work. Okay, so for the next two release, we will focus on the quality, the code quality, to have a very strong foundation and performance. And we are going to benchmark the Coluna against C++ branching cut and price next year, I think. But we are confident. And it's a registered package, so you can add it very easily. The code is available on GitHub, and if there is a bug, if anything happens, if you have ID, suggestion, feedback, even on this presentation, you can open an issue, and contributions are welcome. Okay, so that's an open source project driven by at Optima. It's a optimization software company in collaboration with members of University of Bordeaux and INRIA. I would like to thank the contributors of 0.3, Persiflex for block decomposition, Christiana and Diana from the State University of Rio de Janeiro, Teobaldo and Hugo from the Federal University of Paraíba, and Arthur from the Federal University of Fluminense. And I would like to also thank the Mathematical Optimization Society and Région Nouvelle-Aquitaine for their financial support. So that's the end. So thank you.
Thank you very much. I guess clapping on Zoom doesn't really work, but I assume everyone is right now. So we have a couple of minutes for questions. People can probably either unmute and ask a question or put it in the chat and I will read it out.
Yeah, quick question. Do you support cutting stock problems? Because they're a bit more difficult from the branching perspective.
Cutting stock, yeah. You can do the cutting stock problem.
How does branching work in that case?
The branching? I think the branching will be. I think the branching will be bad in that case because we have to do non-robust branching. So branching directly on the column or things like that.
No. Guillaume,
No?
if I can add, you can, if you formulate the subproblem as a flow problem, then you can branch on the arc and you can have a robust branching. So you branch on the transition of the dynamic programming that you use to solve the subproblem.
Okay, I might have to ask you more about that.
Anyone else have a question? Otherwise, I have one. Yeah.
So I was wondering whether you support parallelism or processing on different computers.
Can you repeat, please?
So when you solve the subproblems, are they solved using multiple threads or?
Okay. It's multi-thread.
And do you also explore distributed computing?
No, it's an alpha feature, so it's only the beginning. So it's a very simple test right now.
Okay, thank you.
So another question. Yeah, so do you have feedback on MOI and parts that were particularly good or bad?
I think it's good. Yeah, it's a good package. But we are going to do a lot of benchmark on the next versions, and maybe if there is a bottleneck on Matop interface, we will open some issue. But right now, at the moment, it's we have no problem with Matop interface.
What about adding extra features like being able to query the duals in a callback? Because at the moment we only have like callback variable primal, right? So it seemed like you defined your own callback reduce cost.
The pricing callback?
Yeah, there was a function in there that was querying the reduce cost.
But Okay, it was no, it was easy to do. I think no, it was very easy to do.
So I guess the question is, what features that you currently have built should we integrate into MOI or JuMP?
Okay. I think it would be good if we can put the variable decomposition and constraint decomposition attribute in MOI. Because in that case, we can use block decomposition to do the decomposition on Cplex, the bundles decomposition.
Oh yeah, so then, yeah, because I guess so like one criteria for adding things to MOI is that we want more than one package supporting them. And so being able to do it for Cplex and Coluna is a reasonable.
Yeah, yeah, it will be good. Otherwise, it creates a dependence on block decomposition for Cplex. So.
Miles, did you have a comment? Or?
No, thanks for the talk.
This is also kind of what StructJump is trying to do, trying to define this decomposition.
Yeah, maybe we should follow this up.
Yeah.
Later, we might end the recording, so let's just everybody thank Guillaume for a very nice talk.
So thank you.
Thank you.